Hello again. This week we're going to take a break from pure data. We've had the pure data for the last 3 weeks or so. This time we're going to go back to processing and we're going to start playing with graphics again. But this time, instead of looking at using predefined shapes like ellipses and rectangles and things like that to draw images, we're going to look at bitmapped images, that is using sort of messing around with individual pixels and collections of pixels which make up images. Before I do that, I am just going to point you to a couple of videos that I think you might find interesting. This is part of the kind of video interesting doodad of the week. This one goes back quite a while to 2006. It's called Scrambled Hacks, and it follows on a little bit from what we did with pure data last week. In that it uses audio analysis to recreate audio that's provided via a microphone using samples from a database that's pre-recorded. I won't play it for you now in this video. Instead, I'll just provide you with a link and suggest you watch it. Very short, very entertaining and interesting video, I think, particularly for those of you that are working with the sort of musical instruments for your assignments, but potentially for others as well. And actually, the second video I'm going to point you to is Face OSC. So far in the subject, we've talked about using different devices to get input from the user. We've looked at using the Connect to track the gestures. We've looked at using the X-Touch Mini to provide them with sort of knobs and sliders and buttons. We've also looked at Touch OSC so that you can provide a iPad or iPhone type interface, like a touchscreen type interface for your users. And we've even looked at the Leap Motion to provide gestural interaction using the hands. Another option for interfacing with your users is actually to use face control, and you can use face tracking to enable the position of your user's eyes or their mouth or whatever, or the position of their head in relation to the frame of video that you're taking to control things. So Face OSC is a nice little app for you to use to do that. Again, I won't play you the video, I'll just point you to the couple of links here which show you how it works. The first one shows you how to link up Face OSC application and the tracking information it provides, how to link that up to sounds. And the second video sort of shows you how you can use it to do face substitution. There's a couple of quite popular sort of phone and tablet apps that do this kind of thing as well. But it could just be another option for you to play with for fun and playful interaction with your users for your users with your app. Okay, so the reference for this week, pretty much everything I'm talking about comes from chapter 9 of the processing book that we were using in previous weeks. So if I suggest you check out chapter 9 and work through the examples and so on that are in there. In this video, I'm going to be touching on some of the important concepts from that chapter. So far in processing, we've focused on vector-based images, that is, shapes like triangle, rectangle, ellipse, and so on, and also curves, and you would probably recall the Bezier curves and things like that. However, if you want to deal with things like photographs and videos, which we will get to in the next few weeks, then we need to work with bitmapped or raster images. And what a bitmapped or a raster image is simply a grid of picture elements or pixels. And what that boils down to, of course, in computer terms, is a grid of numbers that describe the colors of each individual pixel. So to explain this, I'm going to use the concept of a picture frame. This is it's kind of an impression of a picture frame. You have to imagine that the black part is the frame and the white part here is sort of empty. And we can imagine we're holding up this picture frame in front of some scene that we want to capture in the computer somehow. And you can imagine if you hold this frame up over a scene and you hold it steady over a scene that's not moving, and if you look at the very top left corner up here that I'm pointing to with the mouse, if we look at just that top left corner, we could take a look and figure out what color is just that very top left corner up here. And you might look at it and think, okay, well, it's orange in the scene that we're looking at. So we would have to come up with, in order to get this into the computer in a way that computers understand, in other words, in numbers, we would need to come up with some scheme to convert the color that we're seeing into a number. So a very, very simple scene might be that, say, red is the value 0, orange is 1, yellow is 2, green is 3, something along those lines. We can work through the spectrum and allocate one number to each color, and we would then end up with the numbers from 0 to 6, I think, red, orange, yellow, green, blue, indigo, violet, and we could use those numbers as our kind of our coding scheme. So if we would go back to our picture frame that's looking at this scene, we decided that the very top left pixel was predominantly orange. That means we would write down that our very first pixel value in our image would be 1, which is the color with the number we've associated with orange. We then might look at the pixel value next to that, the pixel next to it, at the sort of the next little square of color that we can see through our picture frame at the image we're looking at, and we might say, oh, that's red, so we'll put that down as a 0. Red is 0. We look at the next little part of the picture frame, and you might say, oh, that's orange again, so we'll put down 1. The next part of the frame, that could be green, so we'll put down 3, I think, is our color for green. And we work our way along, allocating a different number for each color that we see at each section of this picture frame. And if we continue doing that all the way through for every little tiny bit of all of the picture frame, you can imagine we'd end up with a very long sort of, well, we'd end up with a big grid of numbers, and each number would represent the particular color that is in that particular part of the image that our picture frame is looking at. And that essentially would be the data describing a bitmapped image. It's just a big collection of numbers describing the color of pixels in an image. Here's an example of a super simple bitmapped image made up of only 2 colors, and we have a color scheme here where 0 refers to the color purple and 1 refers to the color yellow. So if we have an image that looks like this, mostly yellow but with a diagonal line of purple, the data that would refer to that image would look like this: a whole lot of 1s, but wherever there is purple, we have the value 0 instead of the number referring to yellow, 1. So there's a super simple bitmapped image using just 2 different colors, 2 different numbers. But of course, when you're looking in the real world on computers, on modern computers, you're looking at very many more pixels than that. And we're also looking at using much more sophisticated color schemes than just a single number between 0 and 6. We're using a lot wider range of pixel colors. So if we look at this image, for example, an image of a tree in front of some blue sky and in a nice field, if we zoom into a particular part of that image, we zoomed in enough that we could start to see the individual pixels, individual pixel elements like this. We might pick this particular pixel element and take a look at it, and we would see that that has RGB values. In this case of R, the red component is 137 out of 255, green is 196, and blue is 138. So these are the 3 numbers that refer to the color of this particular pixel. which happens to be x81, y123. And the pixel next to it has a slightly different shade. It's still kind of greenish, but this one has different RGB values, and the one next to it has different again. So every pixel in this image would have its own unique, well, not necessarily unique, but would have its own color value associated with it. But again, the concept is the same. We're still looking at a big grid of numbers. It's just that now we have a much wider range of numbers for each pixel, and we have a much larger number of pixels in this image. So that gives us greater accuracy in the colors, and it gives us a bigger or higher resolution image. So that, in a nutshell, is what a bitmapped image is: a big collection of numbers that describes the color of a whole set of pixels of an image that we're looking at. In the next video, we're going to look at how we load images into processing, and how we start to get access to these individual pixel elements, and how we can mess with them, in other words.